Welcome in this video where we're going to implement the famous Adam algorithm. So I believe you use it very often and therefore it's important to know how it works. So we'll implement it in about 100 lines of code and these are the results we get by the end of this video. So this is the testing accuracy on the MNIST dataset is a function of the epochs, and we are comparing our implementation with the PyTorch implementation and we can see that the results are truly similar. In our previous video, we implemented a neural network from scratch, just using NumPy. That means that you can combine the previous video with this one, and therefore you'll have a pipeline implemented from scratch. Okay, so let's move on. We'll use PyTorch as usual, and we will use Keras to load the MNIST dataset, as well as Seaborn and Matplotlib for plotting the results. We can start by loading the MNIST dataset and normalizing it between 0 and 1. And then we can create our class for the Adam optimizer. So we take as input the learning rate on beta 1 and beta 2 as well as epsilon. So these are the hyperparameters described in the paper, and we'll try to implement it by following the pseudocode from the paper so that it's easy to understand. Okay, so we take as input the neural network that we need to optimize, so a model, and we can store it, and we can also create the first momentum and the second momentum. So because the model parameters are not encoded in the same tensor, because they have different shapes, they are encoded. We have a generator where we can iterate over the parameters of this model, and therefore we create a list with the first momentum and the second momentum for each of those tensors each tensor storing the parameters of the model. And we initialize them to 0 as is mentioned in the pseudocode. Then we can store the hyperparameters, and then we can create a function, a zero grad, which is a function you use very often if you are using PyTorch to set back the gradient to 0. So basically what we do, we iterate over the parameters of our model and we set the gradients to 0. Now we can implement the algorithm from the paper, so the step function, and basically we just implement the equations from the paper. Again, we need to be careful that the parameters are not encoded in a single tensor. They are encoded in a list or in an iterator of tensors, and therefore we need to update each tensors one by one in this for loop. Once this is done, we can, once we've computed those intermediate variables, we can move on to do the gradient update. So we iterate over the model parameters and over the intermediate tensors that we've created, and then we update the value of the parameters of the model. We need to be careful to do p.data or not p. If you just do p equal p minus this value, you will not have results. The parameters will not be updated. You need to do p.data to update the value of the parameters. So now we've implemented almost all of the paper. We can move on to implementing the remaining of the remaining needed to test it. So we can, for example, create a train function to do a supervised learning. So we take as input a model, a PyTorch model. That could be the model implemented from scratch in the previous video. We take as input an optimizer, so the one that we've just created, on a loss function, some epochs on the batch size. So we iterate over the epochs. We sample a batch of data from the training sets, and then we can compute the log probability that is predicted by the model, and use the negative log likelihood loss to compute the loss, and then we can do a back propagation. So first we call the zero grad function from our optimizer. We backward the loss to create the gradients, and then we do optimizer.step to update the weights of the neural network. And what we can do is every 100 epochs is to do some testing so that we can see the performance of our model over time, and we can also compare different optimizer, for example our optimizer on the one from PyTorch. Once this is done, we can put everything together. So we can create the device. So by default we'll train on the GPU if a GPU is available, and otherwise we'll train on the CPU. Training is very fast. So we can create some labels to create our figure. So basically, these will be the labels of each line in the plot, and then we can iterate over our optimizer. So on one side with torch.optim.adam, so the optimizer from PyTorch, on the other side with Adam, so the class we've just created, our Adam function. We can create a model. So in this case, we create a PyTorch model, a sequential MLP, and then we can create the optimizer. So the optimizer, we create, so optim, it's either torch.optim.adam or Adam, our optimizer. When it's our optimizer, we just feed the model. When it's torch.optim.adam, it does not take the model as input, but model.parameters. So depending on which optimizer we have, we give either the model or the parameters of the model. Then we can call the train function to get the testing accuracy, and we can plot the testing accuracy. And then we can just improve our plot by, for example, putting the legend, the X and Y labels, and we can save the results. I really hope this video was helpful to you. If you want more content about machine learning, please subscribe to this channel and leave the thumbs up if this content was helpful. It will be very helpful to help the channel. Thank you very much.